All right. Yeah. Thanks for coming today. I'll be talking about how we unified the array API standard with ONNX to provide the ability to export models to ONNX without any explicit ONNX converters. So yeah, I'll get started. All right, so this is sort of what the status quo looks like. If you want to take some model you've trained in whatever library, take scikit-learn, PyTorch, and you want to translate it to ONNX, well, you need to go through a converter. Um, this converter, yeah, thanks. Okay, this converter code is usually kind of somewhat distinct from the actual libraries and code used to develop the library in the first place. So in the case of scikit-learn, you have sklearn to ONNX, which is a completely separate package. In the case of PyTorch, you have the kind of torch exporter, and that's kind of within the PyTorch repo, but uses very different primitives, so stuff like ONNX script to the rest of PyTorch. So essentially, this leads to kind of the need to kind of re-implement parts of the API of the host framework in terms of ONNX operators in order to kind of then support ONNX export for your framework. And this is sort of how it's always been. So nothing new here. This is just the status quo. And this approach really has this inherent duplication to it. You have to re-implement logic, and it's no kind of surprise that this can lead to kind of bugs and missing functionality, because you really have to be on the ball with the kind of API evolution of your host framework when you're developing a converter library. Kind of new kind of iterations on the kind of framework side need to be reflected in your ONNX export capability. Now, this is maybe fine if you can hire full-time employees, or even kind of like have part-time folks working on stuff like torch exporter or something. But if you're developing a new machine learning library for a targeted domain, this is almost a complete barrier to entry to actually support ONNX export for the library you've developed. And somewhat antithetical, I would say, to the promise of ONNX as being this kind of exchange format that's open. So we really want to encourage new frameworks to be able to support ONNX export really, really easily and lower that barrier to entry. The fact that you sort of need to express the ONNX graph in using kind of different primitives to how you develop your library is also another problem. So you need to learn a new tool like something like ONNX script or Sparks to kind of help you construct your ONNX graph. This is just how it's always been. But if I'm a single person developing a new framework, I may not necessarily want to spend my time learning kind of the ONNX kind of tool stack in order to support ONNX export. It might just not be the first thing I have on mind. So what can we do about this? Well, we really want to kind of, from first principles, approach ONNX conversion from a new angle. We want to reduce or even eliminate for a large class of functionality this code duplication. And we want to use the same primitives that you use to develop the framework as that power ONNX export. And at the end of the day, we want to really reduce the barrier for ONNX conversion for newer frameworks and even for existing frameworks to adding new and new functionality to their ONNX export capabilities. And so one of the ways we get there is kind of by hooking into the array API standard, kind of hinted by the beginning of the talk, and I'll just kind of explain what that is now. So the array API standard specifies an API for common operations performed by tensor libraries. So think things like NumPy, JAX, PyTorch, QPy, Sparse, others. And it's really an initiative that began a few years ago, kind of motivated in large part by some of the core contributors of the libraries I mentioned. Introduction to NumPy began a few years ago, and recently you may all be aware that NumPy 2.0 was released, and array API support is actually in the kind of main API of NumPy 2. And so, when you use NumPy 2, well, the API of NumPy 2 is a superset of the array API standard. And this, much like ONNX, is an open standard to define these kind of operations across many different backends. This standard is really promising for library writers for things like scikit-learn. There's a link there where scikit-learn has begun to adopt the array API to enable users to provide their own array libraries, and kind of use, say, GPU accelerated tensor libraries for algorithms that benefit from it. So we thought, we have this standard primitive here that is really kind of important for machine learning applications. What if we build an backend for this? What if we could access the ONNX ecosystem from the array API standard? And that's exactly what we do. But first, I'll show you a quick example of what the array API code might look like. So here we have some this function, mean drop outliers. It takes an array as inputs, low and high kind of scalar values, and as the name suggests, it filters out the values outside the low and high regions and then takes the mean. It's a really basic example just for the purpose of this slides. Yeah, I can't help that it goes. But in any case, you can see here that you can run this same code through NumPy and JAX and not change your application logic whatsoever. And that's really, really powerful. This isn't some sort of duck typing, like this is a standard, right? These operations are standardized. And with ONNX, which is this kind of new library we developed, and yeah, please do go check it out. We developed a backend for the array API standard. So you can now execute this exact same application code. So here in this example, we've switched out the JAX import for import ONNX as NDX, and we've kind of executed that code using an ONNX array. And what that's doing that's different is running it through an ONNX backend. So you could run it through something like ONNX runtime, ONNX MLIR, any backend really, and it's executing it through that backend and getting you the same result. And so we've sort of got a glimpse here into this capability to write code once, have no duplication, and instantly get this kind of ONNX experience from it. But of course, one of the real nice benefits about ONNX is the fact that it's got this file format even. So you can serialize your models to disk, and that's actually really useful when you're trying to vendor your models in production. So for that, ONNX arrays can actually just not contain data. If you just specify a shape, which can be symbolic, and a data type, you can call that same function again. So mean drop outliers, same, nothing's changed. Get another array out, and then just use the ONNX.build function to compile away an ONNX model and save that to disk. And that's all it is. So we've actually just kind of like expressed this functionality once. We can run it through whatever framework we want at train time, NumPy, PyTorch, JAX, whatever. And when we're happy to export to ONNX, we can just do so. We can serialize our graph, ONNX graph, instantly without any code duplication. And so, yeah, so there's an example I've linked below with a slightly more complicated example using a logistic regression model. This is a really, really simple example for the purposes of the slides, but it can get way more complicated, and you can express most things using array libraries, of course. So yeah, I think just a brief takeaway from what we've seen so far, using ONNX and kind of writing your code in an array API compliant way, you can train your code, train your model using all the libraries you love, NumPy, JAX, PyTorch, whatever, and export to ONNX without the need for this explicit converter library. And this is especially useful for library writers who may want to kind of use NumPy, most of the time, but only serialize to disk when you kind of really need it. You get this NumPy-esque API, and it's really an array library first and an ONNX thing second. So you can kind of put your Python breakpoint where you want, use all your Python constructs. There's no AST manipulation. It sort of works just as you expect. And I would say it's also, important to say that the array API, much like ONNX, is an open standard. We're not duck typing NumPy. We're not kind of like trying to track the evolution of some other common array library. No, these are standardized operations that will not kind of change have breaking changes. And so this is really important for us as well. So yeah, I think we've got the main kind of subject out of the way. Like, you get this code reuse, this really nice debuggability, this ability to export ONNX graphs without writing code again. And I just want to talk through a few of the more advanced kind of functionality here. Of course, not everything in the ONNX standard can be expressed in terms of like a NumPy type tensor library, right? So there's things like the LSTM op or the tree ensemble op. And often you want to have this like really fine-grained control of like what operator you're using. And we have this really high-level kind of abstraction kind of here. So we actually have like the ability to completely directly access the ONNX offset and kind of go right back to the ND ONNX array for when you want that convenience and kind of high-level ergonomics again. So there's interoperability with Spox, which we haven't kind of talked about, but Spox is a Python library that allows you to directly construct ONNX graphs, so you can access the exact operator you want from it. And it provides this experimental API for user-defined data types. And I think this is really, really unique in the ONNX ecosystem. It's very exciting for me personally. But you can sort of implement 5 or 6 methods for a new data type. And you have this data type that just works throughout the array library. So at Quanco, where I work, we use it for things like date times, time deltas, categoricals, all these kind of like domain-specific types that kind of allow you to express ONNX graphs at a much higher level of abstraction than you would ever think. And you sort of just have to kind of lay out what this data type looks like a little bit. It's a really short kind of series of methods you want to fill out. If everyone's heard of like the extension array API and pandas, we've kind of taken a few kind of learnings from that. But yeah, I think just to kind of illustrate how far you can take this, you don't just have to kind of stick with array API code and kind of get that code reuse. You can build new libraries on top of ND ONNX. We have done this ourselves. So we built a data frame library that actually implements a subset of the pandas API that we see in our feature engineering at Quanco. And so you see this function right here, compute. It takes as its first argument a data frame, pandas data frame. And there's some relatively high level functionality going on here. Like we clip a series in the A column based on series in the DT1 column, fill the nans with kind of date times and kind of do all this datetime manipulation. And this all just exports to ONNX automatically, by the way. Like you can run it through pandas, you can kind of export it to ONNX. We use this on production models. This is everything in this talk is not like a research project. So yeah, to conclude, please do check it out. Array API code, so stuff like NumPy, JAX, all this sorts of all the fun tensor libraries out there. These can be exported to ONNX with no explicit converter code, provided you kind of stick to the array API standard. And there's this NumPy-like API now, this kind of more abstract way of authoring ONNX graphs. So you're not directly coupled to the ONNX kind of node operator level. And you can build new abstractions like a data frame or whatever, whatever's useful for you. And yeah, there's a link if you want to check it out. But yeah, that's all from me. So I'll take any questions at this point.
Thank you. We'll restrict to one question in the interest of time.
Very cool library, thank you. You show a slide of building pandas data frame, and I was wondering what that resulting ONNX model will look like.
Yes, I should have prepared something maybe. This is actually from the README of the repository. So the graph here, so when you specify a new data type, it looks a little like defining a struct, just a normal struct. So you define a bunch of fields. They could be other composite types, or they could be primitive types that you can see in ONNX. So like a float 32, for example. So I defined a date type that has a kind of Unix timestamp using an integer. And so the ONNX graph itself only sees those sort of basic types. So you don't get the concept of a datetime in the ONNX graph, of course. But in terms of what it looks like, there's a clip operator, there's a bunch of integers flying around, and some masking wheres going on for the Boolean fill nas and stuff. That's sort of what it gets compiled down to. But I don't have a visual representation for you.
Okay, that makes sense. Thanks.
Thank you.